Hello, welcome if you're just joining. I hope everyone is having a good Easter bank holiday weekend. Do feel free to say hi if you're there. I think we're live now, so welcome if you're just joining. I can see the chat, so it'd be great to hear from people today. But we're going to be doing a web class on differentiation. So I'll shortly be sharing the screen and working through some calculus. We'll be looking at differentiation today. But yeah, welcome to anyone that's just joined. Do feel free to send any messages and comments and questions and answers in the chat today. It'll be great to hear from you all. Hi, welcome. Got a first message in there. Hope you're doing well. Hope you're having a good bank holiday weekend. And it's getting to kind of quite a serious point in the school year for a lot of people. Oh, thanks. That's great. Happy Easter as well. That's lovely to hear from you. How is this a topic you've done before? Have you done differentiation before? Welcome to anyone else that's just joined, and happy Easter bank holiday weekend. We're going to be looking at differentiation today. So for a lot of people, that's quite a new topic at A-level maths, really key part of the pure content. So differentiation is quite a big one. It's very useful, massive topic in terms of the A-level. Oh, cool. And some people have seen this before, so hopefully a bit of revision for some people. That's brilliant. Right, we're going to make a start pretty much straight away. So I'm just about to share the slides, and hopefully you'll see the web class content sharing. So let's have a little look. Welcome, as I said, to anyone that's just joined. It's lovely to hear from you. Please do feel free to say hi, ask any questions, and of course, share answers as well in the chat as we go. Right, welcome. Ah, brilliant. Okay. So for some people, differentiation, this is very much revision. It's something you've seen before. That's great to hear. So let me just get ready to get started with this. So we're going to be looking at differentiation of polynomials. It's also worth mentioning that the calculators you're allowed in the A-level now do a lot of the definite integration for you. So if you're not aware of that, that's a really good thing to check. And I'll be talking about that later on as well. I'm Max, a maths teacher. I've been teaching for the last 8 years or so now, GCSE, A-level and below. So it's been a really interesting few years with the changes in the course as well. But calculus and differentiation is very much like a key part of the A-level and has been for years. So I'm going to talk a bit more about this towards the end. But we've got A-level crash course seminars coming up very soon. And these are a real kind of key part of each year. I've really enjoyed these. The last few years, these have been brilliant preparation for the A-level exams. So we go through meticulously through all of the content. So this is coming up for all the sciences and maths during the Easter holidays. As I said, I will mention this towards the end as well. But if this is something you didn't know about, I'm happy to answer any questions and tell you a bit more about that later. So what we're going to do today for the differentiation stuff is we're going to understand what a derivative actually is, differentiate kind of the more simple polynomials, and then some slightly harder ones with some exam questions as well. I'm also happy to talk about calculator skills and techniques and tricks and kind of hints for the exams that can help us, because there's a lot of keywords that should signify to us that we need to do differentiation. So as I said, do feel free to ask any questions, also share any answers as we go. It sounds like for a lot of people this will be revision, but it's really worth going over. So let's have a little look. We'll make a start. In terms of just sort of the basic prerequisite knowledge, hopefully we all have a good understanding of gradients being a kind of rate of change. So if you had two coordinates on a kind of linear graph, we think of it as the change of y over the change of x, and we think of like the gradient as being the steepness. Now that's very much the kind of basics of this that you guys have probably seen at GCSE or maybe even before. But we take this idea a lot further with calculus, and we look at the gradient functions to deal with the steepnesses on curves, which of course is something that's evolving at every single point. So hopefully that's what we recognize by this topic, gradients. So for this part, we can see that the gradients are negative, and then there's something really kind of crucial happening at this point here, this stationary point, turning point. The gradient is 0. And then here, its gradient is positive, and it gets steeper. And we're going to look at what's going on with this and also the kind of significance of this topic as well. So regardless of whatever exam board you're with, whether you're with AQA, OCR, or EdXL, differentiation and gradients is a crucial part of the course. It really does grow into kind of the pure 2 content. For those of you that are in year 13, you'll know that this is just a massive topic. There's first principles, there's lots of different rules, but it all revolves around gradients and rates of change. And it does also filter into the mechanics content as well. Cool. So we'll make a start and we'll look at kind of the basic derivatives of a polynomial, and do feel free to share answers in the chat as well. So if we look at a function, the derivative of a function f of x with respect to x is basically defined as the rate, and this is what we need to kind of almost appreciate more than just the word gradient, the rate at which f, the function, changes as x changes. So I kind of mentioned exam technique earlier, but there are a lot of key words that would signify to us and should be screaming out that it's differentiation. So for example, tangents, normals, perpendicular, gradients, rates of change, all of that stuff is an indicator in the exam that we need to differentiate. Okay, so this is the notation. Hopefully we're familiar with that. Great. So for example, if we look at the following, the derivative of a function at a point can be found from its graph by essentially finding the gradient of the tangent. And this might be the technique you used at GCSE, some of you. So finding the gradient of the tangent. But it's kind of a bit of a clunky way of doing it. And we can be a lot more precise for curves because we can look at what a derivative is. So finding the gradient of the tangent at that point. So you might have done this at GCSE where you use a ruler and then sort of just look at what the gradient and steepness is doing. As we can see for this graph, which looks like a kind of cubic graph, the derivative here would be positive because it's going upwards. And then it sort of gets less positive and flattens off to having a gradient of 0 at this point. And we denote it with f dash of x. Has everyone seen that notation before? And then again, the derivative is greater than 0. So the idea of a rate of change tells us what the steepness of the graph is actually doing. So as I said, I know that some of you have done lots of this and are probably very aware. So just a very quick recap of the basics. If we're differentiating x to the power n, there's 2 very easy steps, and I'm sure you guys will know these and be familiar with these. But the first step is to basically multiply by the power. And then the next step is to drop the power by 1. Brilliant. So if you guys know what you're doing, let me know in the chat the derivatives of each of these, and then we'll talk about what they actually are and what we've found. But it's really good. Hopefully this is a nice kind of easy recap for a lot of people. So reduce power by 1. So for example, you would have nx to the n minus 1 if we were differentiating x to the n. So this first one here, the derivative of x squared, what does that simply become? So the original power was 2. We're going to times by the power and drop the power by 1. Superb. Thanks, guys. Right, straight on with it. Hopefully we're nice and confident with this. Well done. Spot on. So hopefully this is really the start of derivatives, but we should recognize and still be very careful as we get to some of the weird quirky cases. Superb. So 3x squared. And we've got to just keep track of those 2 different things for these polynomial functions. So if it's the power of 3 times by the power, drop the power by 1. And all of these follow that exact same pattern. So we'll whiz through and write all of these down and just check you agree with me here. So that's they're kind of quite nice routine ones to do. Now we have to be a little bit careful with some of these. So differentiated x, what happens there? So if I have the derivative of x, if I differentiate x with respect to x, what do I get? Absolutely, superb, it's 1. And if you think about it, if the graph was y equals x and we differentiated it, the gradient would always be 1. So we would expect a linear function to have a constant gradient. Superb, really, really good. So what about if I was differentiating 1? What's the derivative of a constant? What's the derivative of 1? Super, right, brilliant answers in the chat. I'm just trying to keep track of those as well. Right, so if I have 1, the constant 1, and I differentiate the number 1, so not x this time, but instead 1, the derivative will actually be 0. Really, really well done. And the way we can think of that is that this technically is like us asking to differentiate 1x to the 0. Because x to the 0 is 1 in disguise, isn't it? The 0 comes down and cancels it. So basically, constants disappear. Yes, well done. Right. And that's fantastic that some of you are kind of keeping track of what the process is for integration and what the process is for differentiation, because they're kind of the two halves of calculus, but they're the reverse of each other. And as you go on through the pure content and it gets much harder, it is really important about being precise which way round we do it. Really, really well done. So this next one, 64x to the 63, do we agree? And then this one, 99x to the 98, and then so on, 256x to the 255. Brilliant, right, excellent. So let's just push on a little bit further and then we'll look at some exam questions, but this is great to see how confident you guys are with this, because I know there's lots of different rules that kind of emerge as we go. So if a is a constant and we have a times a function, then if we were to differentiate it, the constant is still there, and it basically just gets multiplied by the derivative. So if it was 2x squared, then there's a 2, but you'd still differentiate x squared and times it by 2. That's kind of what we're saying. And very simply as well, if you've got two functions, the derivatives are just the derivatives. Yes, superb, absolutely. So this one here, all we're basically saying is just differentiate each individual part. Be careful of minus signs, but work it through. So if you guys want to have a little think about this one, we've got some sort of high power polynomial going on. The first few terms go up to x cubed and then it jumps to x to the 19. But we'll follow this process. The 10 will become 0. The 3x will become the constant 3. 8x. Yep, superb. I think this will be minus 15x squared. Yeah, check we agree. And then the big one, I think we've got 133 x to the 18. Do we all agree with that? So we've literally just differentiated every single part. Cool. Okay, excellent. So what we'll do is we'll quick checkpoint and then we'll do some exam questions. And I will talk about calculator hints as well here. So let me know just a 1, 2, or a 3 with how we feel. Looking at the engagement in the chat, you guys are quite confident with this stuff. So just give me an indication of how you feel with that. And then we'll push on to some actual exam questions. Superb. Thanks, guys. So brilliant. Excellent. So if I move this on, let's have a little look. Right, so the gradient of the curve y equals 2x squared at the point where x equals 3. So for this first one, if you guys want to quickly work that out, and I'll whiz through and do that as well, see how we go. So we're asked to find, yes, absolutely. So we're asked to find the gradient of the curve where y equals 2x squared when x is 3. So we're basically subbing in 3 to the derivative. So if you were using the y notation, you use dy dx or f dash of x. Welcome if you're just joining. Excellent. So the derivative, as we've seen, some people are flying ahead with this is great, would be 4x. Now, what we've found is the mechanism that will get us the gradient at any point we want. And since we want it at the point when x is 3, we can sub 3 into this. So as we've just seen an answer in the chat there, if you sub it in, we will get 12. Superb. So I don't think we plan on going over first principles, but I'm happy to talk about that towards the end if anyone has any questions. We're going through the kind of basics routinely to start with and looking at some exam questions. So the gradient here at x equals 3, gradient is 12. Now, I did just want to say at this point, does everyone know how to do this fully on their calculators? So I know there's kind of a mixture of calculators you're allowed at A level, but you are allowed calculators that will do definite integration and differentiation. So if you've got, for example, the class with the white back one, you can do it on there. Let me know if you have that one and I can explain how to do it. The CG50 also does it. But most of the kind of, certainly the Casio calculators that you're allowed at A level will allow you to do definite integration when you sub numbers in. What won't be allowed is ones that do indefinite, that do it sort of algebraically. Yes. Yes, and do you guys know that you can do differentiation on there at a point? So you can sub them and it will give you the derivative. And the same for integrals if it's for an area. But it only gives you the final answer. It doesn't actually say like 4x or do the algebraic version. It just subs the value in and gives you the number. So yeah, but they are allowed. So they're good for checking. Okay, let me know what calculator you have. So if you have this one, do you have the white back class with? Yeah, okay. Yeah, it's only good for sort of checking because all the marks are going to be for actually carrying it out. So the person who's just asked how you do it, if you've got this one, if you've got the ClassWiz calculator, it's the button just under menu setup. If you press shift, let me know what calculator you have. Oh, the CG50, I think it's one of the functions on there. I haven't got it to hand, but you can definitely do it. I think it's in the main option 1. And then if you scroll along at the bottom, there's an integral part and there's a derivative, a ddx bit. I think you go math and then you go along using the arrows at the bottom. But yeah, have a little look. And yeah, we can confirm that, but you can definitely do that on there. You can let you integrate and do the sum, and you can do the derivative as well at a point. But anyway, for something like this, oh, brilliant. Cool. That's great. So just for checking, it's brilliant. What you'll notice, those of you that have done the exams, obviously the exam boards are aware of what the calculators are capable of. So they'll often ask for the answer of an exact thing in exact form. And sometimes the calculators will give it as a decimal. So it's only really good for checking, but still quite reassuring for exam technique. Now, the next one here, sorry, I've got a bit sidetracked. At a point A on the curve. Oh, brilliant. Thank you for that comment. So that's hopefully helped out for the CG50. Or the kind of calculator advice is kind of handy. So at a point A on the curve, y equals 2x squared, the gradient of the normal is 1/8. Find the coordinates of A. Now, this is a really good question. This is very much like what we would expect to see in the exam. So as soon as you see the word normal, gradient, tangent, rate of change, that should be screaming out, I've got to do differentiation. And we've already done differentiation. We know that the derivative dy dx is 4x. But this question's got a little bit more to it. So if they've told me the gradient of the normal, what does that actually tell us? We need to think about what the word normal means. In pure maths, what does the normal to a curve actually mean? And also, therefore, what does it tell us about the gradient? So who recognizes that as a thing? The normal. The gradient of the normal is 1/8. So how can we link that to the derivative? We know the derivative of this curve is 4x. Yes, absolutely. So the normal is like a perpendicular line. So it's perpendicular to the tangent. So the gradient will be different, won't it? So it'll be the negative reciprocal. Superb. It will times with 1/8 to make -1. So therefore, that means the gradient of the actual curve at this point will be -8. Are we all happy with that? Really well done. Some lovely comments there that kind of showcased our understanding of that. So this basically is telling us that the gradient of the curve or the tangent of f of x at this point must be -8. And that's a solid mark just for knowing that. So yeah, so it would be like the negative reciprocal of 1/8. So therefore, it's the point whereby the derivative 4x equals -8. And so now we can solve that for x. That would be when x equals -2. Okay, and a lot of people would go, there we go, done it, x equals -2. And it feels like we're done. Where have we got to be careful? Where could we all lose marks here? It's very easy to stop there. What do we need to remember to do? So we know x is -2. It did say find the coordinates of A. So I've just found the x ordinate. So what do I need to remember to do as well? You might think this is easy. I know what he's getting at. This is basic. This is fine. But we've only, subbed in the gradient, rearranged, found x, but we've found the x part of the coordinate A. So we also need the y value. Yes. So that's it. So we need to put the -2 as x back into the original function. Brilliant. You guys are kind of taking the words out of my mouth here. So this is brilliant. So we've got that. We sub it back in here. Be really careful not to rush that because it's easy to mess up with minus signs. So 2 times -2 squared equals the y value. And do remember to sub into the original thing. And so we're going to get 8. So that means that A is -2,8. So we found the coordinate on the curve that would have a gradient of -8, and therefore the normal to the curve at that point would have a gradient of 1/8. Superb. Right, let's keep going. We're doing really well. So this one here, it's very easy actually for people who've done more calculus and more of the pure content to use different rules from kind of the pure 2 content here. But actually this question has scaffolded it so that we actually just expand it. So it is actually a triple bracket expansion and then it becomes a really easy derivative. Some people might link this with kind of year 13 content of product and chain rule, but that's like a little bit unnecessary for something we could just expand. So we're going to do this in the way that they've guided us to do it. So for part I, let's carefully kind of triple bracket expand that. So remember the first one is a sneaky double bracket. And then we're timesing it by 3x minus 4. Yeah, exactly. Sometimes when you've got more methods at your disposal, you could actually make it harder than it is. This is easy enough to just work, like expand. So we're going to get x squared plus 2x plus 1. Like we obviously still need to be careful. And this is actually the kind of thing that you almost want to slow yourself down at in the question because you won't spot mistakes after. You have to just be meticulous as you do it. So we're going to get 3x cubed minus 4x squared plus 6x squared minus 8x plus 3x minus 4. By tidying all of that up, 3x cubed plus 2x squared. Oops, sorry, I nearly messed out myself there. Minus 5x minus 4. It depends on your course, but I think it's mostly going to be the year 12 stuff. Although if we've got time at the end, I'm happy to answer any questions. But this is really sort of the building blocks. And so the content for differentiation is massive, isn't it, for the A-level course? And some of you that have covered that will recognize that there's stationary points, concave and convex functions, maximizing and minimizing problems, different rules for composite functions, so chain product quotient, trig differentiation. It does become a massive kind of mammoth topic. We're mostly focusing on the kind of polynomial, but we will look at slightly harder derivatives in a minute, and also in the context of exam questions as well. So just differentiating this really quickly, and then we can move on. We would get, I'm going to use the notation f dash of x because they used function notation. So I'm going to stay consistent with that. Let me know if you've got an answer for this. What is the derivative here? Oh, super. Someone's beat me to it already. Excellent. 9x squared plus 4x minus 5. And the constant minus 4 term will disappear. Well done. Are we all okay with that? Does that make sense? We all happy? Very, very well done. That's great. So let's keep going. So what we're going to do now is we're going to have a little look at reciprocals and roots and tidying up some of these derivatives. And kind of doing the algebraic manipulation at the start is really important. Again, if you've done more differentiation, more of the harder differentiation, it can sometimes put us off the basics a bit. So it's a really important review for us to do. And also not to confuse it with integration. So if we have x, 1 over x to the n, immediately the first thing I'm going to do is write this as x to the minus n. Okay, and this is a much more kind of user-friendly format. Is that okay? I just wanted to check, is the sound coming through okay, guys? Can you all hear me okay still? I know we've just moved on topics, but okay, superb, thanks. So here, what we've got, excellent. Right, so this is now suddenly a little bit more involved. I appreciate that. So we're going to take our time, but please do ask any questions if it gets a little bit confusing. So it's still the same rules in principle that we times by the power and then we drop the power by 1. So if we have something like 1 over x to the 5, we're going to write it as x to the minus 5. And then what we'll do is we do that same rule, we times by the power and then we drop the power by 1. So what we end up with is the minus n on top. And I think this is almost easier to see with actual numbers, because if it's heavily algebraic, it can be a little bit off-putting. So for example, 1 over x, I'm going to think of that as, yeah, no worries. And as we see some examples, it might make a bit more sense, but we're going to look at the tidying up aspect of these questions. So for this one, again, it's very easy to confuse this if you've done some of the harder integration. Times by the power and drop the power by 1. So we get minus 1 x to the minus 2. And then therefore that would become minus 1 over x squared. Is everyone happy with that? Because I think if we followed that, it just basically carries on from there. It doesn't, it just, obviously, there's different numbers and stuff, but that is the process. Is that okay? Yeah, it can be more than, it could just be other numbers could come into play. I'm just looking at some of the chat comments there. But yeah, so we'll do a few more and then we'll look at how to tidy this up. Because it's one of those things that if we rush, it's very easy to go wrong. And the notation is crucial. So let's have a little look. So here, if we times by the power, minus 2, drop the power by like 1, be minus 2x to the minus 3, or hopefully we're all happy, minus 2 over x cubed. Ideally, they'll often want it kind of in that form. So hopefully that's clear. Let me know if you guys have got the next one. So 13 over x to the 13, we've got to be careful here. So I would rethink this. So we're like sort of reimagine it as 13x to the minus 13. And what do we get here? I think, just check I'm right, minus, is it 169 over x to the 14? Do we agree with that? Does that make sense to everyone? Yeah. Now, the next thing I want to just talk about, and it's again, it's more of an exam technique and not letting things put us off. This suddenly looks way harder to some people than it actually is. This is just about tidying it up at the start. And because it's all divided by x squared, they've just given us this really clunky way of expressing this thing. X cubed divided by x squared is x. 4x squared divided by x squared is 4. X over x squared is x to the minus 1. And then that would be 5x to the minus 2. Does everyone get that you can do this? Because sometimes with addition, we have got to be careful. Yeah, yeah. So you can, because they've got a common denominator, you can think of them as like lots of little fractions with the same denominator separated. Where we've got to be really careful is if we have something like this, you can't just like do something weird with that where you go x um over x plus 5 and 1. Oh, you can, you could do that, but you can't split the denominator. That's the key thing. But anything on the numerator over that can be dealt with separately and simplified. So that's what we did. And then suddenly it becomes a much easier derivative. So now, if we were to go through, super, excellent. And guys, thank you for all the answers and comments and helpful feedback in the chat. Because actually some of the calculator techniques, it's really great to share those in there. So really well done with that. So very quickly with each of these, if I was to differentiate x, that's 1. The constant term 4 will disappear. This will become minus 1 x to the minus 2. And then this will become, just check we agree, minus 10x to the minus 3. And obviously you could put those back as fractions. Brilliant question. So this one here, why is this 5x to the minus 2? So you could think of that as 5 over x to the minus 2. So if we were to do these all separately, like x cubed over x squared, that would cancel. 4x squared over x squared, that would cancel. And then x over x squared is 1 over x. But what we're saying is 5 over x squared, this last bit, would simplify to 5x to the minus 2. Does that make sense? So, okay, good question. So, um, in general, I would say just look out for if they ask for it in a specific form, because like that is the correct answer. That is right. It's equivalent. And most mark schemes will say OE, which means or equivalent. It's only if they very prescriptively or specifically say, write it as a single fraction or combine it in this way. And depending on if there's more to the question, it's sometimes better to tidy it up. But that's fine. Like as far as I'm concerned, that is the derivative. So, okay, brilliant questions. And this is really important actually for exam technique, engaging with the kind of finer points. So really well done. The other thing I will just say on stuff like this is whilst it's not particularly difficult maths, tidying up, hopefully, it's very easy to tidy a lot of stuff up and then convince yourself you've done the question and forget to differentiate it. Like we've all done that before. So just be really careful if there's a lot of tidying up, almost revisit the question, sort of have a little checkpoint and think, what was I actually doing again? Differentiating, right, now go through it. So this one, this wouldn't be too many marks, but what it's likely to be is part of a bigger question. So it'd be maybe a couple of marks, but it depends on sort of how involved it is, because we can imagine it could be even worse. It's normally going to be more marks if they start asking you to write it in a particular form. So we're going to move on to look at some of these now. Brilliant. Right, now this one, again, is revisiting like our index laws and powers and stuff. So the nth root of x. Yeah, okay, that's a really good point. I'm just kind of looking at some of the questions coming in on the chat. I would say like have a glance at the overall question as an exam technique. And then basically just focus on the bit you're doing. What I would say as a general exam technique, guys, is actually if you open the A-level maths paper and even question 1, you look at it and you think, no, not feeling that. It's not, can't engage with that. Turn over. Don't sit there looking at the question, reading it through loads and loads of times, because I think quite quickly when you see a maths question, your brain already kind of engages with how much work it's going to be. And what is really good as a strategy is to just move on, do the next question, and get in a bit of a rhythm. Because what you forget is your brain is actually sort of subtly thinking about the questions it knows it has to go back to. So if you open question 1 and you just think there's too many words, there's too much going on, read it, pause, and then just turn over, because it's kind of that's a really important strategy, I would say. But yeah, let's whiz through this one, and I think we'll have plenty of time to talk about exam technique as well, if we need to. So we'll just look at these. No worries, that's all good. So x to the like root n. This is well done. I think some people were suggesting how we make this more user friendly. x to the 1 over n means the nth root. So if it's just the square root, we can hopefully appreciate that as we're looking for the derivative of x to the power of a half. And so what we're going to do, times by the power, drop the power by 1. And what we've got to be really, really careful with these fractional ones, it almost sounds silly because it's like a number thing, but when we're sort of bridging that gap across 0 and we're taking 1 away from a fraction, we have got to be really careful. So for a half, it's not too bad, but we've got to be really careful with some of the later ones. Now, also do be aware that we could write this as 1 over 2 root x, because if you think about it, that is like 1 over x to the half, or root x. So you could write it in that form. But again, at this stage, that answer is fine. That is the correct answer. Now, this one we need to be really, really careful with because it feels like almost virtually the same thing. And it's the power of a third. So we're going to have a third x. Now, we've got to be careful with the power. 1/3 minus 1 whole. If it helps, think of that as 1/3 minus 3/3. Because 1 whole, like you can write it in a sneaky disguised way, of 3/3, it's a little bit closer to 0. Yes. So what we've got to be really careful with is that will actually become to the power of minus 2/3. So it gets a bit clunkier. Do we see that? That's a really important thing because off the back of this one, it feels like they're all going to be the same routine thing again, but it's that bridging the 0, it's really easy to go wrong. And like a lot of people could do that and just not even notice. And again, we've all done that before. So just be really careful with, if it helps, the way to do it is think of when you're taking off the 1, think of it as 3/3. And then that will help us not make that mistake. So here, like this already looks much nastier. And it's almost again like just slowing ourselves down. Yeah, definitely sneaky. And here you've also got to remember to square the 2. So this will actually be 4, and then this cube root of x would be x to the third, and it's being squared. So this would be x to the 2/3. So I want to rewrite this as this before I even differentiate it. Is everyone clear at this stage that this is just a confusing way of saying this? Does that make sense? Yeah, excellent. Do let me know if not. Super. Brilliant. Right, so for here, and again, I really appreciate the comments and the questions and the answers you guys are sharing. This is really a nice and energized web class on differentiation. So really, really well done. So here, same process, times by 2/3, you're going to get 8/3 x. And again, that same issue, 2/3 minus 1 whole comes out as minus 1/3 as the power. That's right. Yeah. That's all good. So the kind of general rule that we're saying for this, do feel free to like screenshot it for revision. I'll try and make sure I make an accurate note here. 1 over n, and we've got to be really careful with that power of 1 over n minus 1, because that's not always a nice process. So again, we're just thinking about sorting this out into sort of distinct separate terms. So the first step is get that written in a sort of user-friendly form. And the way I would probably do it is I'd probably reimagine that as x to the half. And then because it's division, just minus the powers. So I could think of x to the 2 divided by x to the half would be x to the 1/2 or 3 over 2. And 3x divided by x to the half, and that's like x to the 1. That would just become 3x to the half. Superb. And now x to the half divided by x to the half, or root x divided by root x is 1. And then this would become 9x to the minus a half. And I just want to clarify before I move on, is everyone okay with that? And don't worry if you think that might have taken me a bit more time, or I'd want to make sure I get that bang on. That's almost the harder bit than doing the differentiation. That's just like, we need to be solid that that is clear. Super, brilliant. So if we were to now differentiate this, times by the power, drop the power by 1, keep going through that process in our head, we're going to get 3 over 2x to the half. what's this going to become? 3 over 2 x to the minus half. The 1's going to disappear. Minus 9 over 2. And this is where we've got to be careful. Minus half minus 1 is like minus 1.5. So the minus 3 over 2. Absolutely, sorry, just to clarify. X squared, did you mean this bit? I'm just sorry, I've only just re-looked back at the chat. Yes, okay, no problem. So yeah, that's how we thought of it, and thank you for the explanations and questions. Think of x squared over x to the half as that bit as a subtraction. So it's basically like x squared divided by x to the half. So you minus the powers. So you could think of 2 minus a half as 1.5, but I think we're better working in fractions because decimals get a little bit annoying. So, and again, if you want to do subtraction of an integer and a fraction, you can think of 2 as 4 halves, minus 1 half is 3 halves. But yeah, really, really good question. So it's almost that same trick as we said down here, where you kind of common denominator it, and you turn any integers into fractions with the same denominator. Very, very good. So let me know how we feel with that, and then we'll look at a couple of quick exam questions just to consolidate like how this could come up. So very quick checkpoint. So I just appreciate, let me know how you feel with those slightly harder indices. Oh, okay. So absolutely the same again. It's a fantastic question. If the coefficient was just different, you would also just include that in the multiplication. And it basically, if it's fractional, it will just affect the numerator. So if it was like 2 over x, or that would be 2x to the minus 1, it's just like if you have a fifth and you times it by 2, it's 2/5. You just affect the numerator. But we'll see that as we go forward. Yeah, brilliant. These questions are fantastic, and the answers and comments you're sharing. So thank you guys. That's really, really good. Some nice emojis there and indications of how we're feeling. So brilliant. Right, let's look at this exam question. So sometimes you're even given a function where you don't know what it would look like as a graph necessarily, but you can still differentiate it and do loads with it. So first thing is actually find the derivative. So we've got the function is x plus 3 over x. Now again, I'm going to rewrite that into a user-friendly format. And I think this actually addresses one of the questions we just had. Are we all happy? That's the original function written in a way that's better for differentiation. We haven't actually differentiated it yet, but it's kind of good to go now. It's ready to be differentiated. Yeah, okay. So the derivative f dash of x would go to 1, and this would become times by minus 1. So minus 3x to the minus 2. Superb. Yeah, definitely. So that's the first part. So if you are, like I said, if you are just tweaking how it's written, don't forget to then actually differentiate it. So the next bit, yes, that's right. So some people call it f prime or f dash or whatever, but it's just notation if you're using functions. So in different kind of realms or parts of mathematics, there's different ways of denoting. Like physics, they sometimes use dots for derivatives, but yeah, f dash or f prime, that is a prime kind of symbol. So that tells us to differentiate the function. Yes, so let's have a little look. So find the gradient of this, and then I'll just check if I've missed any questions then. Yeah, okay. So for this function, so this is actually just a completely separate question. We'd do dy dx. And again, that's the function y. So let's actually just do this from scratch. Let me know if you've got it. Right, so good question, Anna. So basically, I would say if they use y, use dy dx. If they use f of x, use f dash of x. Just try and keep consistent. F dash of x or f prime x and dy dx mean the same thing. They both mean the derivative. They both mean you've differentiated. But just try and keep consistent with what the question used. So in part A, they use the function 1. Part B, they're using y. So I'm just going to stay consistent with what they've used in the question. Yeah, that's great. Is that okay for everyone? The process is the same. And it wouldn't be terrible if you did. It's just better if you can sort of stick with the consistency of what they've done. So this would become 5 over 2 x to the, I remember we're minusing 2 halves off because we're minusing 1 off. So it'd be 3 over 2. That's the derivative. That's the mechanism for finding the gradient at the point there. And we're going to sub 4 in. So 5 over 2 times 4 to the 3 over 2. So 4 to the power of 3 over 2. Well, the half power square roots it, which would be 2, and then we cube it, which would be 8. So we're finding 5 over 2 lots of 8. So 4 times 5, so that would be 20. So that would be the gradient of this curve at that point. Yeah? So it's not so there's a good question. It's not so much reverse differentiation. The reverse of differentiation probably would be considered as integration. But what the questions can sometimes be a bit in reverse, where they ask, here's the gradient, find the point. Or going backwards, like we did earlier with like a normal or a tangent, there can be a lot of reverse processes in in how they present the question. So that's superb. You have got to really keep like be really careful in what way round. Am I subbing in or am I solving? Absolutely. Integration is the other massive part of calculus, but it sort of piggybacks this topic. This is kind of like appreciating differentiation first is really crucial. Right, let's keep going. We're doing so well with this. I think we're pretty much there. Let me just check. Just this, yeah, this little bit, and then there's a few other things towards the end we'll have a little look at. So very quickly, if we just differentiate these, so part A, now they haven't actually called it y or f of x, so let's just do the derivative. What I probably would do is I'd rewrite them first. So I'm going to say that's x to the 4 plus 6x to the half. Make the question nicer for myself. And this one, let's think of this first of all as sneaky double bracket, x squared plus 8x plus 16. We're all good with that over x. It was like x plus 4, x plus 4. We've got to look out for that. And then we can divide that through by x, which would be x plus 8 plus 16x to the minus 1. Okay, that's fine. I'll try and answer any questions like that shortly. So I'll keep pushing on. But yeah, there should be a bit of time, no problem. Right, so what we'll do is if we differentiate this first one, times by the power, drop the power by 1, we're going to get 4x cubed plus, have I done that right? Yep. Plus half times 6, so 3x to the minus a half, which you could write as 3 over root x if you wanted. And then part B, if we differentiate this, we're going to get 1, the 8, the constant term will go, and we get minus 16x to the minus 2. So hopefully the actual derivative bit wasn't that bad. Okay, so really, really well done. Now, so what we've done, hopefully certainly for the pure side of it so far, we've looked at what a derivative is, differentiating simple polynomials, and also when they're not just indices, they're not just like positive integers, when they're fractions, when they're negative numbers. We've dealt with all of that as well. Now, some people were asking in the chat, like for kinematics, which is the aspect of mechanics to do with movement, how does this come into it? And if we think about it, what a derivative is it's a rate of change. So it's to do with gradients. And now if you remember from mechanics, if you have displacement time, the gradient is the velocity. So if it's a constant gradient, like this, it is actually suvat. And if you think about it, so if this is distance, and this is time, then the gradient will be the acceleration, because it's the rate of change of distance with respect to time. And that is still the case if it's a curve, but how do you deal with the curve, how do you deal with gradients with a curve, you have to use differentiation. So when there's quite a complicated thing going on in mechanics with the motion, and its velocity or its acceleration is doing something as a function of time, you have to turn to calculus. And that's how this part of the course gets applied. So yeah, we will have web classes on that in the future, but it's a really important application actually, and it's kind of where calculus emerged from. So Newton and some of the other main players in mathematics needed to kind of create a way of using maths for solving physics problems. And that was basically it. That's where kind of calculus has come from. So yeah, so I'm happy to answer any more questions. But I did just want to mention, first of all, say thank you so much to everyone for all the questions and answers there. We're getting to a crucial point in the year, as I mentioned. So we're very close to these crash course seminars that are coming up. A really enjoyable experience every other year that I've done this. I've really enjoyed taking part in these. They've been quite full-on days, but really kind of hopefully useful for going through every part of the mechanics, the stats, and the pure content. And we really look at kind of the trickiest topics, model how to answer the questions in exams, and all of that stuff. So what we've got, you get, if you do choose to take part in these, you'll get kind of a course content booklet that we go through, and we work through the questions and the test practice, and that's all demonstrated, and you can kind of ask questions throughout the day and the sessions. And there's also a tutor messenger if you have questions as we run the sessions, and we can answer that and go over anything kind of live. So these are all coming up. We've got the physics ones very, very soon, the maths towards the end of this week, chemistry and biology next week. And so they'll be in person, but they'll also be live streamed as well. So if you're interested in that, I'm not sure. Maybe we can get that answered and checked in a second. But this is the main kind of crash course we're going to be doing for the summer exams. So that this is normally when they take place, but there will be 2 kind of full-on days of going through year 12 and 13 content. I'll just read through the questions. Sorry, guys. Oh, okay, Anna. So for that question, oh, brilliant. Well done. That's great to hear some people are joining us for those sessions. For that question, Anna, I think you're kind of talking about like, yeah, if you wanted dAdt, depends what derivatives you have. So if you had like dAdr, and then you times that by dr dt, the bits cancel and the net effect is the kind of fraction makes the derivative you want. So it's normally a combination of derivatives that cancel and create the right net effect. But yeah, sorry, I'm kind of flitting between questions here. So yeah, just back on this, if you are interested in these crash course seminars, I know from experience that these work really well. They're really enjoyable days, but they're quite full on, and we really meticulously go through the whole course. So hopefully that'll be useful for everyone if you're interested in that. But yeah, as I said, this would be a really crucial time for most people. So I really appreciate the questions today. Thank you so much for the comments and stuff throughout. I think we're all kind of very aware of how important and applicable this topic is, and it does really grow. So make sure that you don't rush these questions. You slow yourself down, and part A, they're normally sort of scaffolded, but as long as you get the first bits right, you're actually very much ready to push through the question by summing numbers in and just putting it back into a context. So I hope that was useful. Really, really well done. It was a pleasure working with you all today. And it'll be lovely if some of you are joining the course. Obviously, I'll be involved on Thursday and Friday. I'll be running those sessions. So it'd be lovely to see you there or virtually work with you at the end of the week as well. But yeah, keep a lookout for the YouTube sessions coming up as well. Good luck with all the revision and all the hard work at the moment. As I said, it's kind of getting to crunch point in the year now, but really, really well done. And yeah, absolutely. Thanks very much. Have a lovely rest of your bank holiday weekend. I'm going to stop sharing that there. But really, really well done. And take care. Yeah, happy Easter. Have a good Easter weekend. Well done. Take care, guys. Keep well, and hopefully see you at session soon.